Hey guys, so today we'll be going over torque, specifically rotational equilibrium, and we'll be doing that first of a paper slide where we'll work part B of question 3 on the mechanics section of the AP Physics C 2013 FRQs. And then after that, we'll show you guys how to set up a lab where the physics lab with a lever setup, and that'll show you how to demonstrate rotational equilibrium. So without further ado, let's just start off by going over what is torque exactly. So torque is the rotational equivalent of force. And we know that force is equal to mass times acceleration. So so if you take a rotational equivalent of each part, so the rotational equivalent of mass is moment of inertia, of course, and the rotational equivalent of acceleration is obviously angular acceleration. Then you get torque equals I alpha, right? From there, we look at the net torque, which is the sum of all torques. So the sum of all torques will be the net torque. Okay, and from there, we can start doing the problem. So part B of question 3 involves finding the linear acceleration, which is going to be just A. The setup we have is you have a ceiling, you have a disc, and then you have a string going around both sides. This is someone holding it up, so it'll be applied force. The mass is going to be 2 kilograms. Mass of a disc, that is. The radius of a disc is 0.1 meters, and from earlier we found the applied force to be 12 newtons. So let's just start off by doing a free body diagram. So let's just let this be our disc. We know that there is a tension force from the string here going up, and we know that there's applied force, just because we see it right here, going up as well, and then of course there's force of gravity that always brings everything down. So first of all, let's just find the angular equivalent of everything. So we know that F of A plus T, so torque, so tension force and the applied force are both going up, so let's just make those positive. And then we know that the force of gravity is going down, so let's just make that negative. So mass of gravity. And we know that that's equal to net force, which is equal to ma, right? Okay, well from there, let's just take a look at the rotational side. So considering the sum of the torques, we can see that it equals 0 just because it's not moving. And you have Fa of r, which is applied force times the radius, minus T of r, which is the tension times the radius. And I'm putting it like this because they're going in opposite directions. It's arbitrary, you can switch it up. And then since the mass of the disc is going in the opposite direction of the applied force, it's going to be negative as well. So I alpha. Okay, well at this point, let's just do some quick substitution. So first of all, we know, let's just rewrite this, such as Fa minus Tr is equal to Ia. So we are moment of inertia times angular acceleration, just so we can get it by itself. We know the angular acceleration is equal to the linear acceleration over the radius. And then we want to substitute in the moment of inertia, which we know to be 1/2 mr squared, and this should be in your formula sheet. Okay, well let's just cancel everything out. So we get Fa minus r, because we're canceling out the r's, right? So we can cancel, there's only going to be 1 r now, is equal to 1/2, and these r's actually cancel out since it's r for r and you get 1, so you get 1/2 ma, right? Hey, wait a second, I recognize this 1/2 ma comes from earlier, right? So by adding the two equations, we can isolate ma to be, let's see, so ma plus 1/2 ma gives you 3/2 ma, right? On the side, that should be a t, not r. The t's cancel out, so you're left with 2Fa, and then you have a minus mg here, so you have a minus mg. Okay, well what do we want? We want A, right? Linear acceleration. So let's just isolate linear acceleration by itself. So first of all, you want to divide both sides by m, so you have Fa minus mg over m. Okay, well, let's take a look at those 3 halves. You multiply by both sides by a reciprocal, and this side will cancel out, and you'll get a 1. So you multiply this side by 2/3. Well, everything's going to double, so you have 4FA times 2mg, and then you have 3m on the bottom. Well, we said earlier that FA is equal to 12, so this is just substituting in 12 newtons minus 2 mg, mass is 2 kilograms, gravity 10 meters per second, and over 3 times the mass, which is going to be 2 kilograms. And if we calculate it all out, we'll see that's 1.47 meters per second squared, and that'll be your answer. Now, let's just go on over and check out how to set up a physics lab. Okay, so we're going to just go over a quick demonstration of rotational equilibrium, and I'm going to show you guys all the equipment for it, how to set it up, as well as demonstrate a couple of things having to do with rotational equilibrium. So first of all, we're going to be going over the equipment. Right here we have a physics stand, like you can see right here, physics stand. Conveniently, you have a leveler back here, and if you can see, it's a little bit off right now. From there, we have we can screw in here, and then here is the lever that we will be using that will go on the mount. It's really easy to assemble. The specific screws we'll be using is one this gigantic screw, 307 for this stand right here, and then from there we'll have a 2-part nut and a screw for the lever right here, and there's a specially made part right here that's supposed to reduce friction. It works and it doesn't work. Okay. Now, the other thing that we'll be needing for experiment is one is a protractor. This specific setup doesn't come with a protractor, and you can just take any common protractor and put it here, and I'll show you how to attach that, so it'll be easy to take that for experiment. Second of all, we'll be using this mat set for the experiment. In this mat set, there are 4 of the 100 gram weights, 4 of the 50 gram weights, 4 of the 20 gram weights, and then 4 of these teeny tiny 10 milligram weights. And then for the actual assembly itself, we'll have these, there's 4 hooks that come with this, and then they have 100 milligram bases. Now, okay, so let's put this together right now. So, like you see here is the end of the screw, and here's how I screw it. So, I highly recommend you have somebody else to help you, but I will be doing the solo, just to demonstrate how you can do it solo. Like you can see here, just keep it straight, make sure you get angle correct. You want to keep it side a little bit for the first part at least, just so you can use this side to tighten it. And then once it clogs up, which it will clog up, and then like it's just get in and then go on the other side. And then don't make it too tight, just in case you strip it something, but you want to make it nice and tight, you know, just keep that fit in it. Okay. So after that, you want to put a lever on. You'll see right here we have string on already. This set comes with a big yarn of strings. I'm bad at tying knots, so we put this on preliminarily, but it should be relatively easy for the casual user. So right here we can see that it's semi-level right now. So just pull the screw in on the side, and then the nut goes on the back of this. So you want to make sure you can see you're viewing from the side, so you can see the hole going in to make it easier yourself. And once it goes through, you can turn it back around and then start using a knot. Now, the main problem right now is, well, how are you going to get this protractor on? Because if you have to put this the whole time right here during the experiment, it'll be very inconvenient, right? So, in actuality, my workaround is to just, number one, make this go horizontal, so we can check and see, hey, is our protractor level, right? And then too, we're going to fit into this little gap we have right now. Tiny little gap, so just pin it. Y'all do make sure it's level and then turn it horizontally so you make sure it's correct. Now we see right here that it's not on center and it's also backwards, so we can just turn back around and then get it centered. And okay, and then have a little wiggle room so you can adjust it. And then turn it back around and ta-da, you have your setup. Now of course you can have it how slow as you want. I want to keep it around my elbow level, or not my elbow, my shoulder level, so I can see this easily, but it's up to you really what you want to do specifically. So the first thing I want to demonstrate is just, right now it's in equilibrium, so as you can see here it's at 180 degrees. Now we see a little slight tilting. That's due to the weight of this, and you can just see how sensitive this setup is from this. And as we remember from the rotational motion, the system is at equilibrium with a net torque equal to 0. So you have the same amount of weight on the side and this side. So the center of mass on both sides, of course, it's going to be in the center. So at about 20 centimeters from the origin. And from there, we can see that the torque on both sides is equal and opposite, so it cancels and you get a net torque of 0. Now, just to demonstrate how it works with weights, we have these 200-gram weights, right? And we're going to attach one on each side. So say about at 20 centimeter, because that's where our center of mass is. And like if you can pull one way, like you can see, since there's basically no friction on this, the only thing that's holding on basically is the weight hitting the stand. Now let's go over here and put on him and then that's 10, not what's on here. Ta-da! We see it comes back to equilibrium, right? And for this specific thing, we can see that the net torque is still 0 because at both sides it has the same amount of weight, so it has the same center of mass because we put it at the center of mass. And torque increases for both sides, but it's still equal and opposite. Now the last demonstration I want to do is just how torque changes. So right now, if we remove this, then we have it's standing still because my arm is providing torque, but we have more torque on this side because in addition to center of mass here, then you can see there's a weight going down. So thinking about it as a force body diagram, or no, we can see, or force body diagram, sorry. We can put, I'm going to put actually, we're going to put this up to 200, and say let's put halfway, so the center of mass changes now, and we'll put it right here, right? The thing to keep in mind right now is it's in equilibrium. Why? Because it's double the weight, it's half the distance, and let's just do some fancy math right now, and we can see that it's equal opposite and that torque is 0. Now what if we just stabilize this equilibrium? Let's just use this 10 milligram weight on the side. In that case, we can see, hey, we get instantaneous tilting. And how do you fix that? Well, since it's half the distance, like we did earlier, you guess it, we're going to put 20 milligrams, double the weight, and ta-da, it should come back to rotation equilibrium. And the whole time I think it was at rotation equilibrium because if I look at the center of mass, then it's the angle that it's formed is 180 degrees, so I know exactly where it is. Okay, so that's about it, guys. As you can see, here's a setup of a physics stand and a lever, and we're demonstrating the concept of rotational equilibrium with multiple weights on both sides. Thank you guys for clicking here, and hope you like and subscribe and come back for more videos.